Okay, so I see some questions on the chat. I think everybody also see the questions. I share my screen. So it's 10:30. We will start our lecture. I will answer at the end of the lectures. We will stop 15 minutes to the end, and we will have uh, all the questions that come to your mind regarding the lab B5, also about lab test 2 and the final exams, any other issue related to the course. We will try to answer these at the end of the lectures. We will stop the lecture 15 minutes before the end time, and it will be open discussion. I will share with you all the latest information, and I hope by the end of the lecture we have more students also joining us on this lectures. So today we will start by our lecture by announcing that we have decided to have lab test 2 online on March 30, 2020 at the beginning of the lecture. So we guarantee that all the students enrolled on section O, they are available at the lecture time, and we will have online exam for all the students. Currently we gonna use the course model to run this exam. I will talk more about lab test 2 online version at the end of the lectures. Now let us go forward. But before I go forward, I would like to make sure that oh, screen stop sharing, or okay, everybody can see my screen. You can say yes before I proceed on the chat. You can no. I will try to share the screen again. Okay. I hope now everyone can see my screen. Okay, perfect. So we are back online because it's very important to have the screen on because we have the lecture. I have already posted the lectures. If you go to the course model, I have the lecture already posted on the Eco 360. So if you go to the course model, you will see that inside the Eco 360, the lecture note is here on the lecture 11. And if you click on it, you will see all the lecture note. You can view the lecture notes. And also this Eco 360 help the students. I wish you can see some tutorials provided by the university or some general tutorial, because this is a common learning softwares like Moodle. So you will find other university also using Eco 360. So you can see how you can benefit from this as a student, because it can help you to promote a study plan. For example, you can mark any note, you can put any questions on the slides if you don't understand any part of the slides. So it will help you to generate a study guidelines. So I will leave this for you now, but I would like to mention that the lecture notes is already posted on the Eco60, and also the video for the lecture note 10, it's already there. And once this recording is finished today, I will post the video also at Eco 360. Now back to our lectures. So I hope still the screen is on. So last time we started discussing our collections in lecture number 10. And we discussed the interface and what we mean by interface at the top level. And we said that the interface contains the method signature without definitions. And once you would like to implement the interface, you provide the detailed implementation. As we saw, we have a drivable interface, and the car implement the drivable interface, and also the bicycle implement the drivable interface. The same style we have it for the collections. We have interface for the list, and the list implement this interface, and we have also interface for the set, and the set implement this interface. Today we will continue discussing our collections, and also we hope we can touch the topic of computational complexity, and we discuss some elementary instructions and big O notions and some common category inside the big O using the collections. Again, you can, I will stop after a few slides. I will ask if you have any questions. You can unmute yourself and ask questions, or you can write it on the chat where everybody can see the chat, and we can answer your questions. So remember that whenever you create a class inside Java, you create your own data type. So the person, when one class, it's a person data type. So whenever you create a class, you create your own data type. And inside this class, you define some attributes. Here we have a person class that we discussed last lectures. We have string name, and we have string ID, and we have integer as an age. So we group some set of attributes, some informations all together in one class. Now we are working with a data type called person, and this data type contains three attributes: name, ID, and age. Not only that, also we have built a constructor that create an object for us from this data type. When we define an integer data type or int primitive data type, we know that once we assign a value to this int, we are controlled by the type of this value. We define the data type at the beginning of our course as a set of values and set of operations that control these values. Here we define our own data type is called person by grouping some attribute all together, and we have to give a way to construct this data type. Then we provide some other methods, which is the behavior for this. We can ask this data type get name, get ID, set name, and set age, for example. Also, we can print the data type to the user by asking to string method, overriding it, and so it's retain a string data type where it's printing the data type person to the user. Another behavior we can add it to our own data type is equal behavior. When you want to say two persons are equal, you look actually if they have the same ID based on these. Let me see if I can add. So here we are saying that if the two persons are equal in terms of the ID, we're going to return true. Otherwise, the persons are not equal. And you can see the ID is string data type, so we are using with equals. So both string are equal, then we retain true for this users. Now we have a student data type. Is another class we created. It contains string student name and also integers as student ID. We create a constructor for the students. This is our own data type, so we have to let the computer how we can construct the students. To be able to construct one object from the students, you need to provide the name and ID. If you want to ask the students get name, it will retain the name. Get ID will retain the ID, and we have the print method. We can print the data type called student to the user by asking two strings. So that's will print it to the users how we can print it. Again, here we add another behavior. If you would like to make two students are equal, they are equal if they have the same ID. As you can see here, the ID is a primitive data type, it's int, and we are using equal equal, not dot equals, because it's a primitive data type. Now we have another data type we add to our collections of data type. We create a class called rectangles. We have the width and the height, and we construct the rectangle by using a constructor where we give the width and the height, and we assign the width height for the attributes. We can ask get width, get height, and also we can calculate the area. We can calculate the circumference of the rectangles. These are a set of behaviors with our own data type, which is a rectangle. We can ask if two rectangles are equal. As you can see here, the two rectangles are equal if and only if both the width and the height are equal to each other. Not only that, what I want to say, if the width and the width of two rectangles are equal and the height are equal, then we can say this rectangle, two rectangles are equal. Now, the behavior for this method equals method might be different from one application to another application. In our current definition for rectangle here, for example, we are saying two rectangles are equal if the widths are equal and the heights are equal. Maybe in some other applications, you say two rectangles are equal if their area are equal. So you're not really, it's not important that the width is equal to the width and the height is equal to the height. But you are saying as long as the area of these two rectangles are equal, then I will say these two rectangles are equal. You can say might be the width is 4 and the height it's 3, so this gives you an area of 12. And you have another rectangle where the width is 3 and the height is 4. It's swapped, but again it gives you the same area. You say, oh, these two rectangles, from the point that I say two rectangles are equal if the area is equal, then I say these two rectangles are equal. But based on our current definition for the equality of two rectangles, these two rectangles are not equal. So before I go further, it's very important for me that all of you understand that whenever we define a class in Java, we defining a new data type, and this new data type is an object data type. You will have all the control on how you create your data type by creating the constructors, and you have all the control to define all the set of behaviors by defining methods on this data types. Anyone have any questions on these three classes: person, students, and rectangles? Any question? Okay, Git class, it's not actually, it's our scope here on this course. You will cover it on 2030, but I can tell you, Git class, it will retain the class name. So it will retain actually, this is Git class of this object. So you are taking here, as you can see, we define an input argument as object others. So the name of the variable is others and the name of the class is object. Object is the parent class. Any class you define it on Java, it's automatically inherited from object even if you didn't say that. So all the classes that we define is inherit from the object. Inheritance, it's not our topic on this course, but if you can go to the Android Studio, you can ask to generate equals method by default for you. To be having equals, there is some set of rules that we have to follow. One of these rules, we need to make sure that they are not alias. For example, here this conditions will check if the two of this condition will check if the two objects are not referring to the same object. So if you have aliasing, that means the two variables are referring to the same object, so you return true. Now, if the other is equal to null, or it has different class than the current objects, then you're gonna return false. Like you are trying to compare a student with a person. There is a totally different data type. So get class here, it will let us know that we have a person class. Here in this case, we have a rectangle class it will retain a rectangle. This will retain, for example, other dot class. You are sending, for example, a person object. You are saying, oh, I would like to make if a rectangle is equal to the person. Here we are saying if the get class is not the same as get class of other, then we say we retain false. We cannot run this equality because uh, running a rectangle is equal to the person does not make sense because the attribute inside the rectangle is different from the attribute of the person. Inside the rectangle we have the width and the height as an attribute. Inside the person we have name, ID, and the age. So we cannot make this equality run. And if this is true, if this is not true, I mean, then we have to go to the second line. The second line allow us to cast other to rectangles. So we can access the width and the height of this. We guarantee that we are trying to make equality between two rectangle objects. So we can cast it now manually. Other, we cast it from object, we move it from object here to rectangles. So now we are sure that this other pointing to a rectangle object, so we cast it so we can able to access get width and get height. Again, get class, you don't need to think too much about it. Is the only thing is to check that you are trying to make equal between a rectangle and another rectangle. If you find in these conditions get class is not equal to each other, that means is not equal, as you can see here, is not equal, then you have to return false. This is not making any sense. You're trying to make equality between a rectangle and the persons. Okay. Any other questions? Okay. So let us now proceed. So last time we discussed the list, and just to highlight the main issue about the list, list is an order collection of values, and it will keep the object added in the same order you are adding the object. So you always add at the end of the list, unless if you specify, I would like to add this element at a particular index. So the list will allow you to add the element on sequence. So if you have the samples are coming in stream, you can add it to the list. So it will be added to the end of the list. And you can access the list using the index. You can retrieve the element at index 0, element at index 1, element at index 3. And also you can go to the list and you say, okay, I would like to add element at index 2. It will shift all the element from 3 up to the end to the right and make space for the element. So you can control how the elements are inserted inside the list, and if you don't want to control that, it will be automatically at the end of the list. So list hold the objects exactly as they are entered by you as a user. You create the list and you control how the objects are stored inside the list. If you would like to store the object at index 0, you can say add, you give the index and you give your object, it will be added at the beginning of the list. If you would like to add at the end, you just say add and you give the object, it will be added at the end of the list. So without any reordering or editing mechanism. So this list does not have any internal mechanism to reorder or sort out the element inside it. Again, if we before we proceed, I would like to also to mention list, set, and maps. All of these work with an object data types, not a primitive of data types. So as we discussed early on these slides, a class person, a class students, a class rectangles, all of these are object data types. Object data types, and then we can use these object data types inside the collections. Set, we discussed set last time. It's unordered collections. So set does not care about the ordering. The only thing that it's care about, there is no duplications. So you add object to the set. I don't care about the authors. There is an internal mechanism done internally. We don't have any control about it. The only thing we have know about the set is that we guarantee that there is no duplicate on the object. How the set know that these objects are equal to each other, so avoid adding it again, using equals mechanism. As we saw in the previous slides about the class of person, a class of students, a class of rectangle, we care about equality. We say, oh, two rectangles are equal if their width is equal to the width, if the height is equal to the height. Set rely on how we implement the behavior of equality for each classes. So we define our object class and we override the behavior of equality. So the set can recognize that these two objects, these two persons are equal, so we cannot add them again. And any way, or if you try to add a duplicate item to the set will ignore the behavior, it will not create any exception for you. So you don't know that if I'm adding a duplicate item to the set or not. So in general, you are only concerned with whether or not something is a member of the set or not. So that's why the set is very powerful, and sometimes retrieve from the set or add to the set, you can retrieve using the object. There's no index on the set. No, and you don't know who is you cannot use index. Say I would like to get element at index 0. This is not working. You don't have such kind of behavior associated with the set. You can only say get person, and you give a person object. Give me a person equal to this person if it's there. If it's there, it will retrieve the object. Otherwise, it will return null. A map is another way of looking at the objects. You want to do association between the key and the value. So we have this kind of concept. You go to the library where you want to search for a certain book. You go to the search mechanism. You know the code of each book, and then you will be able to locate the book on the shelf. Otherwise, it's very hard for you to go and search in all the books to find what you are looking for. Imagine you are going, for example, to the party city and you ask for a red balloon. And the people on the party city, they don't organize the balloon based on the colors. They just put all the balloon in one bag, all the colors. And you told the officer or the person there, okay, I would like one red balloon. And he'll go to the big bags and spend 10 minutes to find one red balloon and give it back to you. Then you told him, oh, I changed my mind. Now I need 10 red balloons. It will go again to the same big bags where all the balloons from different color are mixed together and try to fetch one of them. But imagine the situation is different here, where the people at the bar city, they make a separate bag for different colors. Say, oh, red balloon in this bag, yellow on this bag number 2, and green on the bag number 3. Now, when you go to the agent at Park City or officer there and say, okay, give me one red balloon, it will become a very easy task for him to go to the bag number 1 where is the only red balloon is there. So he can grab one red balloon and give it to you back. And if you change your mind and you want 10 red balloon, he can easily go and retrieve 10 red balloon for you. So this scenario is exactly what happened to the map. Map is trying to store values associated to the key. As this example, we have in the participant, we have the balloon with different colors. We decide to put them all in list, for example. It is not organized, so I have to go through all this list to find which one of them is red, which one of them is green, which one of them is yellow. But if I was able to store these all the balloon using the map structures, collection, then I will be able to locate them quickly. All the balloon are based on the key of the color. So the red balloon, the key of red, I will store all the red balloon using the key. So this is the concept of the map. Now, as we discussed last time, we say that We have interfaces and a class like ArrayList, class like HashSet, and class like Tree. These are classes. This class, this is an object class. This is an object class. This is an object class. We can create an object from ArrayList. We can create an object from HashSet. We can create an object from TreeSet. But we cannot create an object from interface. These are interfaces. So these are interfaces, and interfaces we cannot create object from interface. We have inside these interfaces only some set of signature of methods. So only the signature of methods inside these interfaces. And the actual implementation for these interfaces is inside these collections. Linked list, we're not gonna visit this in this course. We're gonna focus only on these yellow classes where we're gonna see some examples and implementation. Linked list, you're gonna discuss it further in other courses. Okay, I will visit the questions soon. Let me just continue. Now, the only thing I would like to mention here is that the tree set, we would like to have the set behaviors that the object inside the set can be quickly retrieved and inserted, but we need to visit them in a certain order. So the tree set implement the sorted set interface. Sorted set interface allow us to visit the element inside the tree set in orders. Okay. One more slide, then we see here the interface of the map. We have the interface of the map, and we have what we call is the tree hash map and tree map. The only difference between the hash map and tree map is the tree map implement an extra interface called a sorted map. So it allows you to visit the element inside the map in order. Any question? Let me just see the questions inside the chat. Okay. Okay. Mm-hmm. Okay. In, regarding the abstract, abstract is another type of a class. We say that we can create a class, we can create an abstract, we can create what we call is an abstract class. Abstract list, it's actually another type of class. It's a class that you cannot create object from it. It's similar to the interface, but the only difference between the abstract classes and the interface is you have some set of implementation for the behaviors. So interface, you have a signature of the methods, you don't have any implementations. When you implement the interface, you have to implement everything, but the abstract class, you implement some set of it and you leave other method unimplemented. So the abstract class, again, you cannot create object from abstract class, but it has mixed. You have some method only signatures and some method where you already create a default implementation for these methods. So abstract classes is the same as the interface entail containing a signature of the method without implementation, and the abstract class is the same as the normal class because it contains some method where the body of this method is exists. So it contains a mix. It's coming between the abstract interface is completely signatures. Classes, you have signatures and you have the implementation. But abstract class is between. You have from the interface and you have from the class. But again, you cannot create object from abstract class. Now, the difference between the tree set. And the hash set, as I mentioned, we need the same behavior of the set, but we would like to visit the element in order. And the tree set implement the sorted set interface, which allow us to revisit the element in order. Now, who is specifying the order of object? If you remember back 2 lectures ago, we discussed what we call as a compare to method. Compare to is coming from a comparable interface. Once you define a person, let's say a person class, and you say, okay, I would like to sort the person out. So I can say person A less than person P. Oh, I have to implement the behavior of compare to. So I will ask a class person to implement an interface called comparable interface, which allow me to implement the method called compare to. And inside the compare to, I will say, okay, how I'm gonna reorder my person object. I will reorder them maybe based on the string equality compared to, so that's Elixir order, or logic orders, or I can say, okay, I will sort them based on the age. So the person with higher age will be at the end, the person with lower age will be at the beginning. So you define, once you define your data class, you specify how you gonna sort your object. But again, comparable interface and compare to is not our scope. But the only thing that we need you to understand in this course is that hash set and tree set are both belong to the set, and the only difference between them that the hash set does not care about ordering the objects, while the tree set try to reorder the objects based on the compare to behaviors. Okay. And after the lecture, of course, I'm gonna post the recording for these lectures either on the YouTube or on the Eco 360. Any other question? Okay. Now here is the example. We discussed this example last time. We have the define list. This is the list is in an interface. Is that we can use it as a reference type. We have the angle bracket. We open it. We say person. So we would like to have a list of person, and we give a name. This is the name for our list, and we say a new array list. And these are in the old version of Java, you have to specify here what is the type. So still, if you want to say, I would like a list of person, and you keep the same thing here, it will be accepted. And if you keep it empty, it will be understanding that this array list of persons, because this is a new version of Java. So you can add a person on the right side, and you don't need to specify it on the, sorry, on the left side, you don't need to specify it on the right side. Actually, as you can see here, we define an array list, and we start adding the elements. So person P, and then person A, person C, and person A. So we add person P first, then A, then C, then A. As you can see, we have duplicate item added here. So the person A is added twice. And based on our definition, the list will accept that. There's no problem. We will contain the element, and the element, they will stay on the same order as we add them. So we will see P at index 0, A at index 1, then we have C at index 2, and then we have A at index 3. So we have 4 elements, and we can visit the element inside the list using for loop. And this is an optimized for loop where we don't care about index 0, 1, 2, 3. We just run through the element inside the list. This is the name of the list and the column, and we define, we have P as a person, because this is a list of person, and we print out the person to the users. So as you can see, the elements are printed out in the same order we add them. So we have P, A, C, A. And again, the array list keep the element in the same order and accept duplicate elements. Here is another example where we define a hash set. As you can see, I didn't use the set as a reference type. I use exactly hash set. I will specify that I would like a string hash set. I give the name for the set. It's hash set 1. And you create a collections of hash set. And again, I specify this is a hash set. This is a redundant. But I add it so I can say I want hash set as string. So even if these two examples, I would like you to see that I can say I would like hash set of string on the left side. I give the name and then a new hash set, and then I say hash set of string. Again, you have to see that these are constructor. I ask for a constructor. Don't forget these an empty parentheses here, because this will create a constructor for me, will create a new hash set. Now after this one, after executing this command, I will have a new hash set named hash set 1 with size equal to 0. So the size for my hash set is 0. Now look this. I will start asking, and this is a hash set of strings, so it contains only strings. So I will add element P, element A, element B, and then element E and C and F. As you can see, the hash set in general does not care about the order. It will have its own mechanism. There is an internal mechanism inside the hash set to reorder the object to guarantee that only one object is exists inside the set. As you can see, we have P, A, D, and then we have C. Even the C is added after the E, and you can see the E is the last element. So no one can protect the order of the set. The order of these set related to what we call is the hash functions, and this is not our scope in this course. So the hash functions will allow us to make sure how we are putting these objects inside the hash set. Now, the only thing that we need to know is the hash set guarantee that only one copy of the object exists, and we are care about if the element is there on the set or not. This is another example. We have a tree set. As you can see, I define a tree set of a string. I use the angle bracket, specify this is a string tree set. I give the name and then I say new tree set. I didn't specify here the string. I use the diamond, open the angle bracket and close it immediately, and then I use the parentheses to create a tree set. At the end of this, I have a tree set where the size of this tree set is equal to 0. Look at these lines here. I start adding P, A, D, E, C, and then I try to add 4 copy of F. Then maybe some of you say, oh, this is a contradict with what we understand about the tree set. A tree set is a set where you cannot allow duplicate. Actually, Java compiler will not allow us to, will allow only one copy, but we will not receive any exception because we adding multiple copy of F. So if we would like to print the tree set, we will print the tree set. Now, this is set where we have string. So we will rely on compare to of a string to sort out these string. And we know how the strings are sorted. It will look at the ASCII code of the element inside the string. And as you can see, all of them have the same beginning. And the only difference now is A capital, P capital, C. So the ASCII code of A is before P, and the ASCII code of D before E, and the ASCII code of C is after P. So I have some idea how the elements are sorted inside the tree set. But I know that I have only one copy of that. These will not, it will be executed, but we will have nothing in terms of element inside. So the element inside the tree set will be 1, 2, 3, 4, 5, 6 elements. There's no F duplicate. Now I ask if the element P inside the set, and that's true, I will remove A. then I will print out the tree set. If the element A is still inside the tree set, and we know that the element A, I already removed it here, this will be executed, but it will be ignored. It will not retain null or something. It will say the object is not there. And then I will reprint the set tree set again. So this is the original. We have A, B, C, D, E, and F. This is a tree set. So the elements inside the tree set are ordered based on the behavior of compare to, and we have a tree set of a string, and we know how to order at strings elements. Now, if the P is there on the set, that's true. We're gonna remove A. You see, the element A is removed, and we ask again to remove element A from the tree set, and this element is not there. So the element is the behavior is ignored. So let us see if you have any questions. You can. Okay. The lecture is recorded. Now. You cannot create now the generic data types is not our scope here. What is referred here is that these actually the angle brackets, these is a generic data type. The generic data type will be discussed in details in 2030, but we are using the collections, and we specify that we have to let the collections know what is the data object data type is. So we would like to create a list of a string. So we know the object data type of this list. And Java, the early version of Java, allow you to create a collections with some generic data type. You can say, I would like to create a list of objects. So you can store inside this collections object of type person, object of type rectangle, object of type student. It will be confusing because you create a collection of a generic type of anything. But a new version of Java start to be more specific, and the compiler will help you to check your code. Let's say I would like to create a set of person. So you inside these angle brackets, you specify I would like to have a person collections. So this is a tree set of a person. So whenever I try to add a rectangle to this tree set, it will contradict. For example, here we have a tree set of string. So a string is an object data type. If I try to make a tree set one dot add, I add a rectangle to this, it will create a compilation error. The compiler will stop executing. I will say you are trying to add a rectangle to a tree set that you define as a tree set of person of strings. So that's why we have to provide inside these angle brackets the type of the collections. And these angle brackets, the name of it is a generic data types. Now you can say I would like to specify a tree list of a type that I will create later on. So you can do that, but we will provide a T capital or E capital. There's some notation and all further discussion or using details on 2030. Now, the lecture is recorded, and we will post the recording of this lectures later on. Now, as I mentioned, the collections for object data type. Any primitive data type, we discussed this in the previous lectures. We cannot create a collection of int data type. We cannot create a collection of double data type or a char data type. If you would like to use int, double, and char in your collections, you have to use the wrapping class. The wrapping class of int is integers, a full word with I is capitals. So here we are using the object data type of int. So you can do this, and we have some example later on. Okay. Now we stopped last time on the discussion. All this is was just a review of what we have already discussed on the list and set. Today we will go over the tree set and sorry the map. And we know that we have the map is the association between the value and the key, and we have two main classes, HashMap and TreeMap. The only difference between the HashMap and TreeMap that the TreeMap implement the sorted map. So we visit the element in orders. Now the map is an abstract data types, and just to highlight what the benefit of using the map data type, if you have the dictionary and you would like to look at a certain definition inside this dictionary, you will go alphabetic orders, and then you start as the first letter of your word, and then the second one, then the third one, until you locate the one inside the dictionary. You are using some kind of coding mechanism, and the dictionary sorted out all the definition inside it based on that. So all the words start with A at the beginning, and all words will start with Z at the end. The same thing, you have your phone and you store your friends on in your phone based on their name. So it might be your friend has different phone numbers. Uh, you will locate them based on the alphabetic order, then you specify which friend you would like to call, and then you will retrieve the phone numbers. So these are kind of things we have it in real life. It's actually we are using the map abstract data type for this. And some other languages, they call the map as a dictionary, like Python language, they call a map as a dictionary where they have this key value pairing. But inside, I think C++ and inside Java, we have the map used. Both languages, they use the map. So for each key, we associate a value for that key. And a map interface map the keys to elements inside it. Like you can have this concept if you would like to go on an abstract level. If you see the list actually it's some kind of mapping. You cannot have two elements at the same index. So index 0, you have only one element. Index 1, you have one element. So you can say the index of the list, which is actually invisible for us. We don't have a I mean, we can control, we can ask with what is the element at index 0? What is the element at index 2? But we don't have a control to change the value of index 2 to 3. I mean, the only thing is it's actually fixed for us. This kind of association is a map. You can go to array also. You have the array, you define the array of 10 elements. You say, okay, I would like to have an array of int data type, and I have 10 elements, so I can go visit element by index. This is the same thing, but in the map, we go one level up. We say, okay, the index that we are working with as an integers inside the list and inside the array, we would like to have it as an object. So you try to associate between object and object. You say, now my key to locate the element inside the map is an object key, is not an integers key. This is another way of looking at it. You can have the map where you have keys. You can search inside the keys and you can retrieve the value for the associated with the keys. This is another view. You have the keys, the name of the persons, and you have your favorite colors. It's like a map between them. You try to map between the keys and the values. As you can see here, we have two keys. They have the same value, but we cannot have multiple same keys. So the key should be unique, but the value can be duplicates. So here we have the set of keys. They are unique. We have four keys: Adam, Eve, and Juliet, and Romeo. But the set of values are duplicates. So you can see the Romeo is like the green, and Adam like red, and Eve and Juliet is as they like blue. So this is very important. The keys inside the map should not be duplicate. And based on our previous discussion, what kind of collections that does not allow duplicate? It's a set. So the set is a collection that does not allow duplicate. So it's the best way to represent the keys inside the map as a set. So the set will not allow a duplicate item. While any other kind of collections, rather than the set, you can have the duplicate elements inside the values. So here example, to create this relation, we say I would like to have a map of a string to a string. So the key is a string object, and the value is a string object, and the name is favorite colors, and new map, TreeMap. This is the class TreeMap, and this is an interface reference type. So we create here by this, we create a map that associated between a string to another string. And this would be able to represent this relations between the name of the person and the favorite colors. Now, there's some set of basic methods or basic behaviors associated with the map. You can say put object key with an object value. So you can go to the map and place a value, object value, and map it to the key k. So this value, object, will be associated with this key. This is a very important. If this is already a value of key, it will replace by v. So if you go to the map where the value key is already there, so this put method will update the value. So this is very important. So if you have a map where the object k is there, and you try to say put object k, and you give object v, so this method will go inside the map, check if object k is there, then will be updated. If its object k is not there, it will be add this relation between k and k. Now this is an example where you have, this is before and this is after. So you will add Bob, and we give it the name, the number, phone numbers. So you will search inside the map. Is the key Bob is there? No. So we add a new pair, which is the associate between the key and the value. If the Bob was there, then we just update the value. But in this example, we're trying to put inside a map where the key is not exist. Now we get object k. This will retain the associated with the key. So if the key is not inside the map, we retain null. So this will isolate by, we can demonstrate this by example. So it's explained here clearly. So you have the map, you get and you give the key, it will retain the value of that key. So we try to get pop and we retain the value associated with this key. If there is no key inside the map, we'll retain null. So we saw now bot and get. We have removed k. This will remove the key or the value paired together. So the key and pair value will be removed if they are exist. Okay, and you can see here. So we go to the remove pop from the map, and if it's there, we're gonna remove both and we retain the value to the user. So get and remove, they will retain the value, both of them. But remove will guarantee that this element will be removed, but get will stay, the map will not change. Size will retain the size, the number of key on the list. We know that the number of key are unique, so the size, this is normal thing. So retain the number of key inside your map. So here is the map and the size is for elements. Clear will remove all the elements. Empty will retain true if there is no element inside the map. Contains key, you give a key and you ask if that map contains a key and will return true, otherwise will return false. Here we ask if it contains path and it will return true. If we ask retain contains key max, max is not there, so it returns false. Contains a value. Sometimes you would like to know if this map contains a certain value or not. It will return true if the map contains this value object or not. For example, here we ask if the map contains this number 55-111. If it contains, yes, it contains, it will return true. You can see here the number is there, so it returns true. If the map contains value Joliet, Joliet is not one of the values, so it returns false. Key set, you can ask the map to retain a set, and it's very important here to notice, to retain a set of keys. So these keys here are actually a set because we cannot allow duplicate on the keys. So we retain a set of keys. We can ask to retain a collection, and we say a collection because collection is an interface. We retain a collection of the values. So all the values can be retained here as a collection, and we retain the values of these. Now remember, we can have a duplicate value inside the map, but we can have only one element inside the set. Okay. Any question up to this point? Let us visit the questions on the chat.
Sorry, for the last sentence, which one can be more than one, which one cannot?
Okay, the key is unique. You cannot have more than one key. The values, you can have more than one values inside the map.
Okay, thank you.
Any other question? Okay. Now, as you can see here, we define a map of us, and we open the angle brackets. We have a string as the key, and the value also as a string data type. The name of the map is reverse colors. The type of it is new 3 map. Now, I would like also to remind you that we can use the map as a reference, and we have to specify which class here that implement this map interface, TreeMap. Now we can ask bot, so we put Joliet with the red, so Joliet Y, the red colors inside this map. We can ask to update, because we know that Joliet now is part of it, so we can update the association. We can say Joliet is now liking blue, not red. Now we can retrieve the element associated with this key. So Joliet is the key, and we can get the value associated with the Joliet. If the Joliet was not inside the map, we have retained null. We can ask to remove the element from the map. There is 2 classes implement the map interface, HashMap and the TreeMap. The HashMap class, you remember that it's an efficient for locating the value and inserting inside the map and deleting from the map. So if you are concerned about the speed of your applications on implementing the map in terms of locating the value inside the map, inserting the value and deleting the value, it's good to use the hash map. But if you would actually concerned about visiting the element in a certain sorted order, then use the tree map. At the end of this lecture today, we will demonstrate the effectiveness of each collections in terms of time. We're gonna see how each one of these collections gonna respond in terms of time for inserting and removing. Now, let us see some example about how we can work with the map. So here we define a map of a key string and the value as an integer. The map, the name of it, is a tree map. Now we know that this is a tree map. That means these elements will be stored in some order based on the sorted area for the string. So we put even with 100, Robert with 90, and other students mine with 92, Michelle with 98, and John with 88. And then we ask to print the tree map. We try to get some person that is not actually inside the map. We'll see if we're gonna get exception or not. And we ask to get an element that is actually inside the map. So if you try to print this one, you will see that the elements are sorted based on the key order. So because this is a tree map and you have a key as a string, so you can see that the order is based on the alphabetic order for the key. Now, the map associates the string with a value. And you can see here equal 100, equal 90, 88, equal 98, equal 90, and equal 92. We try to get element that is not actually exist inside the map, and we have null 15. So there's no exception in this line. So the compiler, the Java, will run the get operation and will retrieve null. And once we ask to John for the value that inside the map, we have a tool. We retrieve the value of this. Now, in this example, we use what we call a concept of autoboxing. This 100 is an int data type. So int data type is a primitive data type, is not object data type. And we have here is integer data type. So the Java will do this convergence automatically for us. We don't feel that we are actually putting the int data type or primitive data type inside the wrapping class. We take this primitive data type 100 and we put it inside the object data type automatically for us. So we feel nothing in terms of autoboxing. So this is a behavior, it's called autoboxing. We explained it in the last lectures. Now, this is another example of hash map. We are using the hash map to define another map between the string and the integers. Here we put inside the map London, Paris, New York, San Francisco, Beijing, and we associated an integer value for each one of them. Again, we are using the autoboxing techniques because 15 is an integer data type, and we are autoboxing this inside the integer objects. We ask to display the hash map. We know that this hash map, I don't know any information about how it will be ordered inside. The only thing I am concerned about retrieving the element super fast, inserting, removing, check if the element is there inside the hash map or not. So I don't know how it will be printed. So I ask to print it out. Now I would like here to look at this command here. I create a tree map, but inside the parentheses. Normally, all the previous example we saw the empty parentheses. Here we give a hash map as an input to the constructors that will construct a tree map for us. So I will take the hash map that I have already created. I don't want to rewrite both commands. I have already did this for the hash map. Now I would like to change the structures. Rather than working with the hash map, I would like now to work with a tree map. I can with one line reconstruct a tree map from the hash map that I have already created. So by this command, actually I created a tree map from the hash map. So the content of tree map will be the same as the hash map, but I guarantee that the tree map will be ordered based on the string order. I will print the tree map again. I can ask the tree map, give me the set of a keys. You can see here, I assign it to the set. I retrieve all the keys from the tree map and assign it to the set. And I give the name of it as key set. Then I go inside these keys for loop and I will get all the elements associated with these keys and to retain the value. I retain it here in integer objects. I can put int here. I will do unboxing automatic for me. So I will print it out. Any questions about this example before I go to the next slide? Any question? So we created a hash set, hash map, sorry. We created a tree map from the hash map and we retrieve a set of keys, not a list of keys, set of keys, and we go for loop for all of these keys and we print the content of the tree map. So this is the hash map. You see the order of the hash map. There's no particular order. I have the value stored inside the hash map. The only concern for me here is the element inside the hash map or not? I can retrieve quickly, I can insert quickly, very efficient. Now, if I ask to create a tree map from the hash map and print the tree map, you can see the order. The hash map order the keys. So Pune will become the first, then London, then New York, then Paris, then San Francisco. If I go through the element, the keys, and print them, I will retrieve the keys in order also, because the tree map store the keys in order. Any question? Okay. Now we cover all the three collections: list, set, and the maps. Java expert, they find that there's some kind of set of operation that we do for these collections always and always, rather than implement these operations for each one of these collections. So we implement a version for list, a version for set, and a version for the hash map. They said, okay, why we not create a called collection toolbox, a collection class? And remember, this collection class with S is not the same as collection interface that we discussed earlier. So this collection classes contain several static methods. that operate on the list, set, and maps. One of them, for example, binary search. You would like to search inside your list, or inside your set, or inside your hash map. You try to sort out. You try to find the minimum and maximum inside your collections. You try to reverse the order of collections. You try to shuffle the collections. You try to swap elements at the certain positions. You try to replace. You find an element inside the collection and you try to replace it. So there is also another set of methods. I recommend you to go and Google this collection and try to see what is the set of operation that I can use, but these are the most important operation that we can apply to the set. Let us see some examples here. So these set of static methods are available for all the collection, as I said, and so it will allow us to manipulate the collections. Look here, I create a collections of integers, array list of integers. I add, again, I use auto boxing techniques here. I use array list of integers. I add 13, 3, 5, and 1, 3, 4, and 19, and 222. And I ask, rather than go and have a sort, I can ask collection.sort. So by asking collection.sort, I actually sort out my collection. So all the element inside the collection now, array list, will be sorted. Then I print them out. You can see the elements are sorted. Now the sort behaviors here depend on the behavior of compare to. And we know that Java expert create this integer data type for us as a writing class for int data type. So the order of sorting is clear that this will be ascending order. I can ask to shuffle the collection and print it out. I ask to shuffle again and print it out. So shuffling is we order the object in a certain way, random orders, and I ask two shovels, and then I would like to know the maximum and the minimum of my collections. So you can see here I shovel the array first time, then the second time, and then ask for the minimum and the maximum for my array list using the collections classes. This is another example where we have array list of a string, and we start adding elements inside this array list. The only difference here, you can see I add the same numbers in terms of integer, but I add a string here, students 13, students 3, student 5, and student 1, and student 34, and student 19, and student 22, 222. Then I ask to sort out. So what kind of sorting mechanism I'm going to see here? I'm going to sort out the element inside the array list based on the sorting mechanism that sort the string data type. Because all elements all inside the array list are a string objects. So we will sort out the element inside the array list based on the sorting mechanism of the string. Then I'll ask to shovel two times, one here and another one here. I ask to find the maximum element and the minimum element. The maximum element will follow the maximum in string and the minimum string, because all element inside my array list is a string elements. So if I sort out, I find out string 1 will be the beginning, then string 1, 3, and we know the ASCII of 1, then it's followed by ASCII of 3, and ASCII of 1 followed by 9 is less than the ASCII of 2 followed by 2 and 2. and the ASCII of 3 is greater than ASCII of 2, and the ASCII of 3 and 4 is greater than ASCII of 3, and the ASCII of 5 is bigger than 3. So I know how the strings are sorted based on the ASCII code. And then I ask for shuffling the array again, and I can ask again for the shuffle, and maximum, you can see the maximum is string students of 5, and the minimum is a student of 1. So these are two examples help us to see how we can use the collections class with the list and others. Do you have any question? Any question? Okay. We go now to how we can visit the elements inside the collections. We saw these examples where we have a for loop. We can visit all the elements of the list. We can specify here array list of persons, and I would like to visit all the person inside the list 2. The list 2 is the name of the variable. All the element inside the list 2 of type person, so all for loop for the person p, and I visit the elements. By visiting the array list like this, I'm not concerned about the location of the element. My concern is the element itself. I can find out. I can use the interface called iterators. Iterator is an interface, and all the collections implement this interface. And we can see in this slide the generic data type. I specify E as a generic data type. I can implement the iterator for any data type. So I have the method has next. Next will retrieve the object, and remove, it's an optional. So this is an example where I use the iterators. I have the array list of a student, of a person, list 2. I can say, I give me an iterator of a person data type. I call it it2, iterator 2, and this iterator should have list 2 iterators. So the list 2 iterators will be stored inside I2. And I can say while iterators has next, give me the next element, because this is the method inside the iterators. Iterator is an interface. Only the signature of the method is there. There's no implementation. Each one of these collections, list, set, and map, implement its own iterators, and all of them implement this iterator interface. You can ask has next, that means it has a next, give me the next element. This is where we are using inside these while loop. So this will give us the iterator always retain the state, represent the position inside the collections, and the behavior prompt us to step through the collections. Now, you can use the iterator to visit your element inside the collections. You can use the for loop to visit the element inside the collections, or you can use the standard for loop by asking for I is equal to 0 as long as I is less than the size of the list, or the size of the map, or the size of the set. Give me I plus 1, and you can visit the element inside the list or the map. Now, remember that if you are working with the list are storing the element at index 0, 1, 2, 3, 4. But the set does not store the element at any particular index. You can retrieve the element from the set by providing the object itself. And you can retrieve the element from the map by giving the key object by itself. Now this is our last example to discuss the collections. We would like to highlight in this example is the performance. This is the objective of this example that I create for you, is to show the performance of the set and the hash map and tree map when we are working with very large number. So we have here 8,000 iteration or 8,000 elements we're going to add them. So we start by creating a list of integers and we add element inside this list and we ask to shuffle it. So we add element from 0 up to uh, 7999, 79,999, and then we ask to create a hash set from the list that we already create in the previous step. So we create the list in this step, we add the element to the list, we shuffle the element inside the list, and now we create the hash set. Now we ask get a test time, we'll take the list and we will retrieve that we see how we can work with the hash set, how many milliseconds to get method. We can ask to get remove time if we would like to remove element from the set. This will measure the element of get and this will measure the element of remove. Again, we ask to create a linked hash set. We didn't discuss it, but I put it here for to make it a comprehensive discussion. A linked hash set is another collections, and it's now the scope of our course, but I created here on this example for to make it more comprehensive. And as you can see, I use a collections as an interface reference data type for all of them, because collection is the interface that hash set and the linked hash set implement. Also, I have created a linked hash set. I ask tree set. I assign it to collections. From this list that I created the first step. Also, we measure the get time for the tree set, the remove time from the tree set. We created an array list. We measure get time from array list, remove time from the array list. We created a linked list. It's another collection data type. We measure the get test time and remove time. And these are the method get test time. So we can see here we are going to ask if the collections that we receive contains, and we generate a random numbers, if the collection C we receive here as an input argument contains an element that we generated randomly, and we see the time, and we do this for, as you can see, for 8,000 times, and then we see the difference on term of the time. So we start the time here, we subtract the time to see the time, execution time, to get 8,000 elements, 80,000, and we try to remove from the collections. This is the method to measure the removing time. So we start the time, we ask to remove 80,000 elements, and then we see the time. This is the comparisons. You can see that if we are working with the hash set, we need 3 milliseconds to get an element or to check if the hash set contains a particular element or not. Because if we check the element is contains, that means we check if we can get it quickly. Now we have removed element, we have only 1 millisecond. So the hash map almost very quick in term of hash set, sorry, in term of get and remove. But linked hash set, it's require only 1 millisecond for to get the element and to remove the element. So it's a quick in term of get and remove the linked hash set. If we look at the tree map sorry, the tree set, not TreeMap. The tree set, it's actually fast, but it's still slow compared to the hash set and the linked hash set. It needs 5 milliseconds to check if the element is inside the tree set or not, and 6 milliseconds to check if the element is to remove it, compared to 1 millisecond inside the hash set. Now, if you look at the array list, it's need a lot of time compared to the hash set or even to the tree map. It's need 82 milliseconds to get any element from the array list, and you need 40 milliseconds to remove the element. And all these numbers we see here based on 80,000 elements. So when we say a get element, we say get 80,000 elements. And here the linked list is very slow architecture and compared to the others. So these examples highlight the benefit of using the hash set, using the linked hash set, tree sets, array list, or linked list. And you can see in terms of the time, storing the array list of one element or storing the hash set of one element or array list of one element, you will not be able to see this difference. I hope you can go at home. You already connecting from home, so you can uh, try to run these examples at your home, and you change the numbers from 80,000 to say 100 millions, and you see the numbers become big difference. So if you are trying to create a set where you can put all the citizens of Canada, which one of these structure you would like to prefer? I will prefer to put them inside the linked hash set, or I prefer to put them inside the hash set. I will never put them inside the linked list, because this will take a huge amount of time to retrieve an element or remove any element from this collections. Any questions before we proceed to the next topic? Any question? Let me ask you a question now. If you would like to create a Java application where you would like to store the students and the courses that the students enroll on in, so which kind of collection you are using? So you have the students on one side, and you have the courses on the other side, and you would like to store them. Which one of collections you are gonna use? You already have a create a class of a student, and you already have a class of a course, and which one of these it's the best? The map. That's right. The map is the best choice for these collections, where you have the students as a key, and you have the course as a value. Okay. Uh, Now, someone may say, okay, I will create a new class, and this new class I will have a students object inside it, and I have a course object inside it to be able to store everything inside a set. I recommend the map as a collections to do this kind of relations between the students and the course. So you have the students, one students, and you can have the course associated with that students. Any question before we proceed? Okay. still we have 15 minutes, then we will stop the lectures and we will talk about more about the course, the lab number 5, and about the final exam, about also the lab test too. But as you can see, this example motivate us to see the what we call a time complexity, how we can measure that students write an algorithms and the other students write the same algorithm, both gonna do the same thing. As you can see on this example, both gonna do the same. Collections will store the object. You can get the object from the collections. You can retrieve the object from the collection. You can remove an object from the collections. All of this, hash set, linked hash set, tree set, array list, linked list, all of them gonna do the same job. But which one is the best? This is a question we're going to answer using the time complexity. In the time complexity, computational complexity, in this course, we're going to focus on the time complexity. There's two parts on the computational complexity. There's a space complexity. There is a time complexity. The space complexity related to the memory, how much your algorithm going to take from the RAM and storage when you execute it. This is called the space complexity. And time complexity is about how many unit of time that your algorithm gonna take if we execute it. As you saw in the previous slide, we have measured everything using milliseconds. And I guarantee to you, if you take this example and you run it in your machine, you will have different numbers maybe. My machine is different from your machine in terms of the hardware, in terms of how many RAM I have, in terms of how the internal architectures of my machine is different. So we need a common unit that the developers or the programmers can communicate with it. It's a unit of time. It's not actually a millisecond or 1 minute, but we can say a unit of time. And what is a unit of time? We're going to see on the next slide how we're going to define a unit of time and what is needed to be able, when I look at your algorithm that's contain for loop, if statements, and then creating an array and executing an element from inside array, I can tell the time complexity of your algorithm using the big O notations. What is big O notations or this? We will see this on the next slide. But before I go deep, I would like to remind you all with some kind of logarithm and exponent notations. So we know that log always can be log base 2, log base 10, log base any number. But in this course, whenever we say log, always we mean log base 2. What that mean? That means if I have log base 2 x equal to y, I mean by that 2 to the power y is equal to x. So log x equal y is equivalent as saying 2 to the power y is equal to the x. So log is 1 million is less than 20. Based on this definition, that we have a log x equal y, so x is equal 2 to the power 1. Just to remind you with some mathematical terms. Also, exponents are growing very quickly. Logarithms are growing very slow. So in this graph, you can see the difference not between the exponent, but even n to the power 1 and log n. This for n is growing linearly with the time. So at 1 is 1, at 2 it's 2, but logarithm is growing very slow compared to n. So log n is growing very slow compared to the exponent. And this you can see it even if you take a pencil and paper and you try to say 2 to the power 1, 2 to the power 2, 2 to the power 3, and you can see how much quickly you grow in the numbers. When you are at 16, 2 to the power 16, then it's become very large number. While in logarithm, you always growing very slow. If I have log a times p, this can be divided as log a plus log p. If I have log n to the power k, this is equivalent to the k times log to the power n. If I have log a divided by log p, this is equivalent to saying log a minus log p. This is a pure math. If I have log x, I can write it as log x without the parentheses. This is growing slowly as 2 to the power x, growing fast. So if you have the running time for any algorithm that is a log x, then you guarantee this algorithm is running very slow compared to the algorithm that is running very fast. This is grow very, very fast in terms of the x. So when you change x here between 1 and 1 million, this will give you a very low value, while if you change x from 1 to 1 million, this will give you very, very infinite value, very large. Now if you multiply log x times log x, this is equivalent to log square x. It's greater than log x for all x is greater than 2. So if you have log x times log x, you can write it as log x squared, and this is greater than actually log x for all x is greater than 2. These are floor and ceiling functions. The floor is the integers, the largest integers not greater than x, or you can say the first integers less than x. This ceiling is the smallest integers greater than x. So if x here is 5.1, you take the ceiling. So what is the largest integer not greater than 5.1? It's 5. If this is 5.1, x is equal to 5.1. What is the largest, what is the smallest integers greater than 5.1? The smallest integer greater than 5.1 is 6. So you can use the ceiling and floor to round up or round down the integer real numbers to the integer value. Computational complexity is concerned about the resources as I mentioned. Some of these concerns will be related to the space, how many storage you need inside your computer when you run your algorithm, and some of these resources concern about the time. In this lectures we concern about the time, and these resources always measure by the size of the input, the size of the problem that we are trying to do. And here in this course we are going to focus on the size of the input. If we are talking about the size, we never have a negative size. You can say I have an array of minus 2 elements. No. Always when you have a list or you have an array, either you have 0 or you have n. You never have a minus negative size of the input. So the size of the input or the size of the problem that always you try to solve is an integer value. It's not a fraction. You cannot say I have a list of 2.3 elements. Either you have 2 elements or 3 elements. You cannot say I have an array of 5.9 elements. So the elements inside the input or the size of the input or the size of the problem is always integer positive, not negative. In the real world, we would like to see if implementation A is faster than implementation P on a sub data set C. So you are having two algorithms, A and P, both gonna do the same thing, both are compiled successfully, both are running and give you the right output, but you would like to know if implementation A is efficient or running faster than implementation P. This is back to the our example when we compare the behavior of the hash set and tree set, linked list, and also the array list. All of them gonna do the same job, but which one is the faster? Which one is efficient than the other one? We will try to address this by time complexity. So if you would like to think about this in abstract level, you think that any method that you create inside Java is actually you created based on the transformation. You take input, you transfer input to the output. Like this algorithms. It's sorting algorithms. It's taking the input, unsorted array, and it generates a sorted output. So you're doing a transformation. So you work with the data, and any algorithm that you come across over is actually some sort of transformation. You take input, you transform input to the output. So running the time of the algorithm always measured by the size of the input. We would like to know if we increase the size, we have an array of 4 elements, how the sorting time will change with respect to the size of input. If I change the number of elements of input from 4 elements to 1 million, what will be the running time? So we try to draw a graph where the x-axis is the size of input and y-axis is the running time of the algorithm. So we are trying to create a function of the size of input, f of x, where x is the size of input. So we have a function now. We would like to come up with this function, and that is the objective of this computational complexity. So this is a set inside the list. You have public static boolean contains the name of the method. We receive an array of int and we receive the value as an input argument. We would like to return true if the value inside the array. If the value is not inside the array, we return false to the user. So this is one of the implementations. One of these implementation is saying, okay, I will do the for loop. I will go from 0 up to the array length and we increment the index by 1. I will visit the element one by one. I will compare the element of the array at index I with the value that I received from input. If I have it true, I will return it to the user and break out from the loop. So once I find the value, I will break out. I don't need to execute a next iteration. If I couldn't find the value, then I will receive false because I defined originally result as false. So if this for loop, I execute this for loop, I visited all the elements inside the array, and none of them is equal to the value that I'm looking for, then I will retain false to the user. Any question up to this point about this implementation? So the objective here is to determine the time complexity, or in other words, is to be able to draw a graph where this line is the size of input and where n the size, and this is f of n, and f of n here is the time complexity. Now in the previous example we run the time based on milliseconds. Now we're gonna run it based on some kind of curve. So we know that if we change the size it will be like this, or it will be like this, or it's an exponent going like this. So we try to draw a graph based on the size of input n as a function of f of n with the time complexity of the algorithm. And here we provide one implementation for the contains method. Any question before we proceed? Okay, so the size of the problem is n is the number of elements inside the array. I will stop at this point and we will open the discussion for the course, and if you have any questions, let me just stop the sharing and also stop the recording.